Good evening and welcome back. This is episode 2 of the BET Masterclass series, Built to Scale. My name is Alicia Britton. I'm a Senior Project Manager at BET Software, and I'll be your host tonight. Before we dive into our insightful tech-focused topic, I'll just take you through some house rules. So the session is recorded, as you can see. It will be shared with everyone who is registered as a replay later on. So if you stay in the session, that means you agree to that. So to avoid disruptions and to keep the focus on the attendees, we have disabled mics and cameras for all attendees. Only the co-organizers and the presenters will have that function. But please use the Q&A chat feature if you've got any comments or questions. Keep it respectful though. Offensive or inappropriate behavior will get you removed from the chat. Our support team will monitor the chat and the presenters will answer any questions during the Q&A segment. So our masterclass series is about sharing knowledge, solving real-world tech challenges, and highlighting the incredible expertise we have at BET Software. And tonight's series is called Data Diaries, Real Data Processing, Strategies and Tools. We'll explore how to manage and process high-volume data streams, a topic that's at the heart of building resilient, scalable systems. So joining us today, we've got two highly experienced presenters. We've got Duane Dicks, a senior dev, over 30 years of experience, especially with technology like SQL Server, Python, Kafka, and Debezium. Duane has led projects across enterprise-scale data systems and modern deployment pipelines. His vast experience in both legacy and modern technologies makes him a powerhouse in bridging traditional and real-time systems. We also have Kayshree Ramdial, a senior dev and database specialist. She's got over 15 years of infotech experience. She works across web development, data design, and BI reporting, and her focus is evolving towards event streaming technologies and real-time data processing. Kayshree has also designed and maintained high-performance databases for large-scale platforms, and she's passionate about turning raw data into business value. She's also an active member of the data community, continuously learning and sharing knowledge to help others harness modern data technologies. So, Kayshree, Duane, we are thrilled to have you both lead us through tonight's session. To set the stage for our discussion, Kayshree will now provide a more in-depth introduction into tonight's topic.
Thank you, Alicia. Good evening, everyone, and thank you so much for joining. I know it's the end of a long day, so we appreciate you spending your time here with us. Before we get into the details, let me quickly walk you through what we'll be covering. We're going to chat about data and real-time processing. Then we're going to have a brief overview about the different event streaming tools and technologies. Next, we're going to chat a little about scaling guidelines, walk you guys through some demos, look at managing schema changes, and lastly, Q&A. So although if you guys do have questions, please do feel free to pop them in the chat and we will do our best in answering. Now to set the stage for all of this, let's first look at the world we're living in, a world where the amount of data generated every second is staggering. And this is where the idea of data overload comes in, right? Let's just begin to understand the magnitude through some stats that I've grabbed online. So there's an estimation of over 180 zettabytes of data that will be generated in this year alone. Now, for those who can't quantify what a zettabyte is, it's actually 1 billion terabytes. I could convert that number for you in terabytes, but we're probably going to have a good laugh as I try to attempt to butcher that figure, which might give off some serious Jacob Zuma vibes. So to save myself some embarrassment, let's just say 1 zettabyte is equivalent to 1 billion terabytes, right? Now, based on that estimation, there's over 400 million terabytes of data generated in a day, right? 90% of that data is unstructured. Unstructured, basically, we're looking at um, documents, multimedia, images, videos, and 70% of that is user generated, which is structured data. So examples of structured data are relational databases like SQL Server. And I'm mentioning SQL Server here intentionally simply because it's part of our demo. Other examples of structured data is your spreadsheets, Excel, CSV files. Now, with data volumes growing at this speed, the challenge isn't just how much data, but how quickly can you detect, transmit, and act on the changes in real time. What is real-time processing, right? So real-time processing is basically the ability to analyze data as it's being generated or received without any noticeable or significant delay. So we're looking at high-speed data ingestion and near instantaneous response time. We're looking at low latency, high throughput. I've listed a few sectors here where real-time data is at the forefront of their businesses, right? So if we look at retail, companies like your Takealot, Amazon require real-time processing to handle online transactions and inventory. Transportation, companies like your Uber courier services rely on real time for vehicle tracking and managing deliveries. Everybody's all time favorite, social media, LinkedIn, Facebook, we require real time engagement metrics. Gaming, right? So companies like your Electronic Arts, Sony, needs real time data processing for multiplayer gaming. Betting companies, right? We need to be able to accept bets, process transactions, and update the outcome as the events unfold in real time. Now, to go from data overload to real-time insight, we need the right tools and technologies. And that's where change data capture, which is CDC, Debezium, and streaming via Kafka Connect come into play for real-time processing. Now, I know that was a mouthful. So before we deep dive into the demo, let's just set the foundation by understanding the concepts that I've mentioned and why they're important in modern data architectures, right? Okay, folks, so I'm going to attempt to build a story here, but please just try to keep up. Fair warning, though, I might just fumble or stumble along the way, and we'll be switching screens a lot. So hang tight, and hopefully we can keep you entertained as we dive into how data flows in real time from SQL Server through Debezium and land in Kafka. So think of this as a little adventure into behind the scenes magic of data streaming, right? So how do we get there? Right? We've got data coming into our SQL Server database. A service is set up to retrieve the data, and consumers subscribe to that service to retrieve the data. Now, do we now need to go off and write a service? No, we already have one, and that's called Kafka. What is Kafka? And no, it does not mean anything, right? But fun fact, Duane's son, Damien, actually shared this with us. So Kafka was actually named after an author named Franz Kafka. His work often explored complex, messy systems. And similarly, Kafka is designed to handle complex streams of data. But Kafka is actually a data or distributed event streaming platform. It's designed to handle high throughput for real-time processing. It was actually created in 2010 by a group of engineers that worked at LinkedIn, and they developed it to address challenges handling large-scale real-time data. And this is how Kafka came about. It was designed to provide a fault-tolerant, distributed, scalable platform for handling high throughput and low latency. It later became open source in 2011. And Confluent is the company that was actually co-founded by the original creators of Kafka. It offers a commercial platform providing additional features and services to enhance the ecosystem. Then we come to producers and consumers. Now, a producer is an application that sends or writes data to a Kafka topic, and a consumer is an application that basically reads and processes those messages from Kafka. So, spoke of topics. Topics are like your database tables, right? So when you publish data to Kafka, it has to land somewhere, and that somewhere is in a topic. Now, the big question, how do we get the data into Kafka? Right? And this is where Kafka Connect comes in. So Connect is basically an extender of Kafka that is compatible with SQL Server, right? It provides connectors to allow you to integrate SQL Server with Kafka. Now, how does Kafka Connect know that there's data coming into the database, right? And this is where CDC comes in. It stands for Change Data Capture. Although if you just Google CDC by itself, it'll tell you it's the Center for Disease Control. And that's what I thought it was. And I heard it a few years back during COVID. I was actually working on a project with Niels Berglund at the time. And he was the one that actually introduced me to streaming technologies. So I know what I know today because of him. So thank you, Bali. But really, CDC is a feature in SQL Server that automatically tracks and records changes made to tables in your database. Now, these include inserts, updates, and deletes. And in order for CDC to work, you need to have it enabled on your database as well as your table. I want to take you guys through a quick overview as to what really happens when CDC is enabled, right? So first you need to enable CDC on your database. And when that happens, two jobs are created in the backend. You get a capture job and a cleanup job. Now, we have our source tables here, table X and O, our user created tables, right? So when CDC is enabled on those tables, an associated CDC table is created as well. And you can see that with the CDC schema. Now, when a record is inserted into the user created table, which is X and O at the top, it's stored in the transaction log. Your capture job then comes along, picks up the records from the transaction log, and sends it to the CDC schema tables. This is essentially the process for CDC. Now, how does Kafka know that there's changes happening in the database, right? Earlier on, I spoke of Kafka Connect, and this is where Debezium fits in, right? So Debezium has two types of connectors. We have a source connector, which basically reads data changes in the database and sends those changes to Kafka. And then we have sync connectors, which basically reads data from Kafka topics and writes those changes to another system. So Debezium also supports a wide range of databases for change data capture. And just to name a few, we've got SQL Server, Postgres, Mongo, and MySQL. Basically, if your database has a log file and a personality, Debezium probably wants to talk to it. I'm going to hand you over to Duane, who will demonstrate how we get data from a SQL Server database on one server all the way to Kafka and to a consumer on a second server. Over to you, Duane.
Thanks, Kayshree. Let me just grab the share here. Okay, so what we're going to be doing is we're going to have, we decided to harvest prime numbers purely because they've got a random distribution. And so it'll provide challenges when we want to consolidate data from multiple sources. So we've created 4 tables. I'll go into that later, but let me just show you what's in the Docker setup. We've got the full Confluent Kafka infrastructure, and then we've got 2 SQL servers. So the first SQL server is going to hold the 4 tables, and the second one is going to hold the data that's been consolidated. I'll just show a quick example. So what we've done is we've decided to chase the first 50,000 prime numbers and process them in parallel from 4 different streams and consolidate them in the correct order on the other side. So what we're going to be doing is we've created these 4 SQL tables. I've called them prime 1, prime 3, prime 7, and prime 9. And the reason for that is after the first prime numbers 2, 3, 5, and 7, all other prime numbers are going to either end in a 1, a 3, or a 7, or a 9. So the processes will literally just harvest, check 11 for prime, 21, 31, 41, etc. And then what we do is I'm going to start them all up in parallel, let them start processing, and then start a custom sync connector. Because they're coming from various sources and the collating doesn't fit into the normal pattern of a vanilla sync connector. I'll just give you an example of what that looks like quickly. So this is the prime numbers that gets generated, and we literally just adding it by 10 each time and checking for prime. And if it is prime, we're writing it away to the database. And in the sync process, what it does is it listens on the topic that we're going to create, and then it writes it to a working area. And how we get the data to land in the correct order is the working area is ordered by the prime number, and because now they've all landed in one table, and then we write away the top 80%, because we can guarantee that that's landed correctly, because the bottom 20% may well be out of order because more data is still coming through, etc. So when I start this up, which I will do shortly, what we're going to do is we're going to just copy those SQL files across. We're going to execute them on the SQL servers. I'm going to create a topic that we're going to publish all the results to. And then I'm going to, just getting back to the SQL Server. In the SQL Server part, I'm enabling CDC on the databases and the tables automatically. And then I'm going to create a connector, which I'll show you what it looks like now, and that's going to harvest all these prime numbers. So what the Debezium connector looks like is I'm basically just going to be routing everything to this topic, and I'm going to be fetching it from these 4 tables as we mentioned. And so all the data from them is going to be routing into the prime topic. So let me start it up and we can see how that goes. Sorry, I'm missing something here. Okay, so it's busy starting up. When that starts up, we will have the 4 processes running in parallel. I'll show you what that looks like once everything's going. I've put a pause in of 20 seconds when I start the SQL Server machines because they don't start that quickly, and I had times when I was trying to write data to them before they'd started up. Okay, so it's copied the SQL files across. It's now going to create the tables and enable CDC across the board. Okay, so there you can see it's created the CDC stuff. That's why it's created those cleanup jobs. And now what it's doing is it's doing the stuff on the destination side where we're going to show the data that's sunk. It's also created a signals database, which we'll be using a bit later in the demo as well. Okay, there it's created the topic with 6 partitions for us, and it started the connectors for us. All right, so now I'll just show you what this looks like. So as you can see, I've got these 4 processes that are busy harvesting all the primes, and they're writing them away to the database. And at the same time now I've started up a sync process, which is going to be reading all that data and collating it into a SQL database. I'll just show you what that looks like here. Let me just connect to the databases. Okay. I went to SQL 1, and I'm going to connect to SQL 2 now as well. Okay. So on SQL 1, you'll see this is those four tables that we're populating, and on SQL 2, we are going to be collating all the data into this table here. Okay. Where we're sitting, we are sitting at almost done. So once those are completed, I'll just show you how the data's landed, and you'll see it should all be touch wood, in the correct order on the other side. I've also added to the tables, I've added a timestamp of when the data landed, and I've also added a timestamp of when it landed in CDC and when it landed on the destination as well. So yeah, while this is running, I'll just show you some of the data landing. Okay, so as you can see, those numbers are climbing up, and at some point we'll land at 50,000, and we can show you the collated information. Seems to be running a bit slower than normal because of, I think it must be the video feed that's on here. So I'm not sure if Kayshree, if you can continue with the rest of your stuff, and when I get back to show the signals, I'll show the collated data, because I'm going to be working on this again as well. Is that okay? Cool,
Yeah,
thank
that's
you.
fine. That's fine.
Thanks.
Gonna take the share again. Thanks, Duane. So moving on, we've covered the core tools. We looked at SQL Server with CDC, Debezium for capturing changes, and Kafka for streaming out. But what happens when this moves beyond a demo, when we start throwing real traffic, real change volume, and real production pressure at it? So the next topic we look at is scaling, right? So scaling involves smart decisions at 3 key stages. The source, which is your SQL Server database, right? The data movement, which happens with Debezium, and the destination, which is Kafka itself. Let's just chat about some of the guidelines regarding SQL Server, or when it comes to scaling at SQL Server, right? Check what you need. So enable CDC only on the critical tables and columns to reduce overhead, right? Index wisely. So proper indexes on your source tables help SQL Server find changes faster. Offload long-running queries. What does that mean? So avoid heavy reporting or analytics on the same server. They tend to compete with CDC performance, right? And lastly, monitor your log retention, your log size and its retention. So since CDC depends heavily on the transaction log, ensure that your system has sufficient disk space to accommodate increased log growth, right? Implement frequent transaction log backups and monitor log size trends to prevent any unexpected disk full issues. We've seen this happen, right? Next, scaling during data movement, right? Split large workloads. So what does that mean? Use multiple connectors for different tables or schemas to spread the load, right? Secondly, tune your connector settings, right? So when Duane did the demo, I think he briefly squizzed over your connector settings. Some of those settings are like your batch size, your polling intervals, and you also have snapshot modes. Now, you can crank up your batch size, right, and reduce the polling interval to make things faster. But if you're working with large tables, that's like trying to funnel a flood through a garden hose. The result, Java heap will come to its knees. Your connector will throw a tantrum, or rather an out of error memory. So polling too frequently on a huge table, it's like checking your phone every 5 seconds, right? You burn out and you get nothing done. But jokes aside, tuning your batch size and the polling interval is just about finding that sweet spot. You want your connector to keep up with the data, but not choke on it. So start small, monitor performance, and scale smart. Right? And lastly, we're looking at scaling at the destination, which is Kafka, right? Use topic partitioning. So break your Kafka topics into multiple partitions so messages can be processed in parallel. Then we have your replication factor. So that basically determines how many copies of each topic partition is stored across the cluster. Now, your default is 3. Why it matters? It ensures high availability and its fault tolerance. So if one broker fails, another one can take over. Tweak your retention. So don't keep too much data in Kafka if you don't need it. Clean up efficiently. The default is 7 days, but this obviously can be adjusted according to your requirements. And lastly, use consumer groups. So downstream apps can scale by reading from Kafka in parallel, each taking a slice of the workload. Now, a common mistake is treating scalability as an afterthought. Don't fall into the trap of let's get it working first and we'll scale later. Scalability should be baked into the design, not bolted on later. So what happens when we need to make changes at the source DB? Maybe we want to add a new table to start publishing through to Kafka, and our connector is already created, busy producing data, and the consumer is already consuming from it. So Debezium detects these changes automatically, right? However, not in SQL Server. I'm going to take you guys through a demo where I'll be showing you how you can add a new table to an already existing connector. I'm going to just share my screen. Okay, so we've got our connector running currently. That's based on the startup that Duane had done. And as you can see, we've got our prime 1, 3, 7, and 9 tables. Now we're going to add a new table to that. Just going to create it quickly. We're going to enable CDC on it. Once that's done, let's just check that it's here. We see prime 11. Do we have our change tracking? Yes, our change tracking is here. So I'm just going to add some data in there just to make sure that we've got something to publish through to Kafka. Okay, so we've got just over 1,000 records. Now you can see how manual this is, right? And this is why Debezium comes with some limitations. Now, in order for me to ensure that this actually is added or appears in Kafka, what I need to do is update or run a put request to our Kafka REST APIs. One of the most important configs here, this is our Debezium connector, by the way, and one of the most important configs here is our table include list. And as you can see, prime 11 is actually missing, so I'm going to add that on. And once I do, I'm just going to try and split my screen here so you can see. So we can see there's no new messages coming through now, right? I've added prime 11, and I'm going to hit send here, right? 200, that's good. Just give it a couple seconds for the data to come through. Demo cards are not on my side today. Gonna try that again. Oh, what we should be seeing here is some records coming through after adding a new table. Just gonna check the status of my connector. It's running. Oh, you guys don't tell me. I'm missing the schema here. That is why. Oh, let's just refresh this and make sure that there's nothing there. I just want to clear this out so when the new messages do come through, you'll be able to see it. Let's try that one more time. Okay, there we go. Om Namah Shivaya. Okay, guys. So I've basically added, and you can see that. So it was prime 11, server ID identified as 11. And that's essentially how you would add a table to an already existing connector that's publishing data through to Kafka. I'm going to stop this, or rather, I'm going to switch Windows now. Cool. So your connector is already running, right? You've got what sort of challenges could you experience in live systems, right? You've got a connector that's running, it's producing a steady stream of events, and downstream consumers are depending on that flow. So in this kind of setup, making any changes or even just trying to reprocess data can be tricky. You don't want to restart the connector, and you definitely don't want to introduce downtime. So how do you safely manage data reprocessing, right? Or trigger a snapshot again without disrupting everything? And this is where Debezium signal tables come in, right? It gives us a way to send instructions to the connector that's live to do things like replay data or snapshot a specific table, all whilst the system stays up and running. So your signal table is a special user-created table on your source database, right? It acts as a control channel for your Debezium connectors. I've got a code snippet here just on what that table structure looks like, right? You have a unique ID, your signal type, which is usually your snapshot, and your data command, which is in JSON, which includes your table list and any conditions for the table specified. So by inserting rows into this table, you can basically send commands or signals to the running Debezium connector without having to restart it. So it's like basically a remote control for Debezium. Now, unfortunately, the Debezium signal table isn't enough to add a new table on its own. As you guys saw, I had to manually go into SQL, create the table, enable CDC, go into Postman, do an update to get that data across, right? Now, what do you do in a situation where your connector goes down and we need to recover, or we need some sort of recovery mechanism, right? Um, and this is where the Debezium signal table comes in, right? It allows us to replay data, which is a really valuable feature, and it's actually a real game changer, right? What would we do if we're in a situation where we need to have some sort of recovery mechanism, right? You can force a change to the source table. It's possible, but it's not ideal, right? And this is exactly where the Debezium signal table comes in. It's a powerful and I think often an underused feature that lets you safely and precisely trigger operations like data replays without having to touch your application logic or your schema. So there's no need for like hacks or workarounds. All you need to do is insert a row into the signal table, and Debezium handles the rest. So I'm going to actually show you guys how we can actually replay data. So give me a sec. So as you can see on the screen, I've got some code, right? Essentially, what we want to do is to instruct the Debezium connector to replay some data for us. So the code includes like a unique ID, which is signal 001, the type of signal, which is a snapshot, and most importantly, the command itself, right? We're basically telling the connector to take a snapshot of the specific table, which is prime 11, and you can also add a condition to it. Now, if you know the exact point in time when your connector went down, you can actually specify from which point you'd like to replay that data. And that's exactly what I'm showing here. So I'm essentially replaying all the data that I've just generated for Prime 11. And I've used this date, which is the 5th of October. Now, I would like to just split my screen so you guys can see the data being replayed. I'm just going to refresh this window. So we see there's no new messages coming through. So a good thing to do is actually bake this Debezium signal table in your initial design. If you guys noticed earlier on when I shared my Postman collection or my put method here, I actually have the Debezium signal table already added. So that saves me the trouble of actually coming and adding it back in here. Okay, let's try this. Time to call on the demo gods. There we go. Does take a little bit of time, and like Duane mentioned, I think it's just with our cameras on. But this is actually how you would replay data, and it's such an awesome and powerful feature, honestly, to have. Like I mentioned, try and bake it into your design earlier on, so we have very minimal manual interventions required for this. I'm going to actually take us back to our presentation. So earlier on, I mentioned SQL Server can do a few things with your connector. However, there are limitations. For example, you saw all the manual steps that I had to do to go and add a new table. And to address these limitations, like where your Debezium signal table is not enough or it cannot be used to add a new table, this is where the workaround comes in. So Duane the Brain came up with this. He came up with the smart mission control system that actually listens to your Kafka topic and is able to process incoming messages to perform SQL operations, interact with Kafka Connect, and execute shell commands. I'm now going to hand you over to Duane. He's about to blow your mind with these custom signal tables. So brace yourself because things are about to get seriously cool. Duane, the stage is yours.
Thanks, Kaish. Let me just grab the share here. So just on that replay that you did with the signal table, that is very, very handy. And it's probably something that if you do work with this, you will have to do at some point in time. In the past, I've done it by updating SQL tables, but this will work perfectly well for as long as the data is sitting inside those CDC tables and hasn't been retained, and it's a beautiful approach. I just want to, sorry, I didn't show you the end of the previous thing. So literally, I inserted one row into each of those tables, and then I did 13,000 on each. And you can see we've come through with our 52,004 rows. And if you have a look here, you will see it's also nicely landed it in the correct order as well. So and that was all done via a nice little clever worker process, which just sends off a finalized 80% at a time and goes off. And then also what I forgot to show was obviously how the data comes through the topics, but Kayshree showed you that. And I'm going to show you how I'll just go through how this mission control thing works. So what we've done is I've created another table, or another 3 tables called signal. So the idea here is Kayshree's referred to this before as like a remote control, which I think is a very good idea, or a very good name for it. So what we want to do now is we want to try and control SQL Server Kafka and Kafka Connect from the beautiful user interface known as SQL Server Management Studio. So what we're going to do is we're going to enable CDC on all of these tables, and we're going to send it instructions by dumping code into this code block. And then we've got it's quite simple actually, this little Python script, and it's going to listen to that topic, which we've called mission control, and if it's a SQL thing, it's going to go and execute SQL work. If it's a connect payload, it'll execute connect work, and if it's a Kafka payload, it'll execute Kafka. So what we're going to hopefully achieve out of this is we're going to change the structure of one of those tables, and still manage with very little downtime, get it to start harvesting and processing under the new structure. So what I'll do is I'm just going to start up that mission control app. So figure out where I am. Okay. All right. All right. So now this is going to be listening to that. So I'm just printing payloads, yes, don't worry about it. This is going to now be listening to that mission control topic, and I'm going to start checking some information at it, and we'll hopefully see stuff happening. I just want to get the code that I've prepared for it, and I'm going to just bring this into Management Studio quickly. Right, I need to be on 2. All right. Okay. Right, so the first thing, I'm going to just test creating tables on the other database from here and see if that works. Okay, so what I'm going to be doing is just inserting a create table command into that table, and hopefully it'll carry it through onto the other side. Let me just show you what the other side looks like. So this is what I call the other side. And what I'm going to be doing is I'm going to be adding that table to this database here. So all right, so I've sent it to Debezium, to SQL Server, sorry, and what Debezium's done is it's picked it up and it's executed it on the other server, and you should see that that table's popped up there now. So if we refresh this guy, there we go. So I was created on the fly, like I did it there. Okay, so now the next thing is I thought, well, let's give it a go and see if we can do the same thing for a Kafka command. And let me just show you. I'm going to create a new topic there, if this works. So just give that a go, and we should hopefully see a good response here. Wait for it to come through, and there we go, and it's created that topic as well. If we go and refresh this, we should see that topic's appeared in Kafka. And there it was. Okay, and now the big challenge is to try and use this type of approach to solve another problem, and that is dynamically changing schema, etc. So what we're going to be doing is I'm going to send code through to stop the connector, disable the CDC, alter the table, re-enable the CDC, and restart connector. And then we should see the topic with new structure, an extra column coming through. So let's give it a go. Let's try, and let me just get the connector page ready so we can check its status and make sure everything's working. So if I go like here, There we see that connector is busy running. Now what I intend to do is stop it from SQL Server, and we'll do it like this. All we'll do is we'll cause call the pause endpoints on Kafka Connect. And let's give that a go. Right, so we should see a stop issue command coming through. It says it's done well. Let's give it a go and see what the status looks like here. As you can see, it's paused it, right? So the next thing we want to do now is we want to disable CDC on the table. And so what I'll do, I'm going to be doing it on this table here. So as you can see, this table exists now because CDC is enabled on it. When I disable CDC, you should see that one disappear. Let's give that a go. Okay, let's see if it worked through mission control. There we go. It says it's done it, so we should hopefully see that that table has disappeared from the system tables list now. As you can see, prime one's gone. So we've managed to disable CDC from SQL Server. Now what I'm going to do is I'm going to alter this table. I'm going to add a column, and we should hopefully see that filter through as well. Okay. It says it's data too, so we'll go across and have a look at how that looks. And as you can see, there's that new column that I've added. It came through nicely. Then the next step is we want to re-enable CDC on that table. So we'll just quickly execute that. Let me just make sure I've highlighted this properly. All right, so that should hopefully have come through nicely here. Come on. Let me send it again, wake it up. Okay, hopefully it comes through now. There we go. So now it's saying that it has it's re-enabled it. So if we go and have a look at this table, these tables here, we should now see that there it's back. And what we will see is it's also got that column that I added. The last remaining thing is to restart the connector, and then we want to hopefully see data coming through under the new structure. So we'll give that a go. I'm calling the resume endpoint. Let's have a look here. It should hopefully have been successful. That says it's all good. I'll do a confirmation on this side to see that it's back to running. And there you can see it's running. Okay, so now what we're expecting to see is in this topic here, we're expecting to see new messages coming through under the new structure. So obviously there's no movement at the moment, but I will just nudge it. I've got to go back to the initial database, to this one here. And I'll just push all 13,000 records updates. Okay, there we go. And now we should see those messages coming through here. There we go. And you'll see they've also now got that new column. And so what we did was very very little downtime, because essentially if this was all run in a script that followed through, you'll have a couple of seconds downtime at most, and that's what we've got right here. So that's it from me, and I'll hand back to Kayshree. Thank you very much.
How cool was that? Thank you, Duane. So that's a wrap on our demo journey. The connectors survived, the data flowed, and the demo gods were mostly kind. Are there any questions before we close out?
I'll just quickly add that this demo is going to be available in a playbook, which will be shared here, as far as I know, and you'll be able to run it as is, so you can start up the Docker instances and everything, and you should hope it'll be like your own Lego box that you can play with.
Well, I do see a question in the chat from Niels. The question is, CDC enabling is highly transactional, or enabling CDC on a highly transactional database, wouldn't that impact performance? So we did share a few scaling tips for SQL Server. Just to name a few, we can only enable CDC on the tables and the columns that we need. We need to index wisely, ensure that our retention on our transaction logs are actually being adhered to. But if the data is available on a separate database, then it's highly recommended to rather enable CDC on that database. Duane, I don't know if you have anything to add to that.
Yeah, just another thing would be our default CDC, I think, is set to 3 days retention, and the cleanup job is set to about 3 a.m. every morning. And if you're going to be working with high volumes of data, you obviously don't want to retain the data for 3 days, like Kayshree mentioned, to make it run through fast. So you must slim that down a bit. And also, what's very good is to, instead of running the cleanup job once a day, run it a few times throughout the day, because if you get to a very busy area and that large job, there's a large amount of data that needs to be cleaned up, the cleanup job ends up locking with other issues, and you start having issues around that. So cleanup job, as simple as it sounds, scheduling that to run frequently makes a big difference.
Duane, Kayshree, thank you so much for your incredible insights. Do you want to pop up your QR code on the screen?
Sure, I just see one last question.
Oh, perfect. Take that first.
When working with Debezium connectors, is there any way to enrich or modify the data before it gets to Kafka without having to make changes at the database level? It's a good question. So when you want to modify or enrich data as it flows through Debezium and Kafka without making changes to your source database, there is a feature in Debezium which is called single message transforms, right? SMTs. So SMTs basically allow you to change the data on the fly inside the connector pipeline. So maybe you want to filter out certain fields, you want to rename something, or even mask sensitive information. And there's no need to actually change this on the source system. Using SMTs will allow you to do that.
There's another one for you, Kayshree.
Duane, do you want to take that one? Is Kafka a server?
So Kafka is essentially well, it's all set up. I'm not sure if you can say it's like Azure servers, but maybe if I just take the share again. Give me a minute. Right, okay. If you can see that, I'll just go to here. So what it is in this case, it's Zookeeper, which isn't always used, but then you can have one too many Kafka brokers, and Kayshree spoke about scaling. So obviously adding more brokers is a form of scaling. You can have one or many connect nodes as well, and control center, which is not necessarily always used, have nodes for that as well. So it's a distribution of multiple servers. They can also live inside like Kubernetes pods, etc. And often it's managed that way in a cloud setup. So hopefully that answers the question or comes close.
I think there's one last one. Does CDC add latency to transaction commits? Looks like Kayshree and Duane has some connection problems. But thank you everyone who joined us for episode 2 of the BET Masterclass. We hope you're leaving with practical strategies for real-time data processing that you can apply in your own work. Before we wrap up, just want to give you a quick reminder. There will be a link where you can download the exclusive playbook, and that's based on tonight's session. It's a handy resource that you can revisit and apply what you've learned. And by the way, if you are in Durban, don't miss a chance to meet Duane and Kayshree at the Data and AI Community Day. It's this Saturday on the 11th of October. It's at Richfield College at their Umhlanga campus. So go ahead and sign up now and connect with Duane and Kayshree in person. So to close off, please go and follow BET Software on LinkedIn. That's where we share updates on future episodes and other exciting tech events. And of course, keep an eye out for episode 3 of the BET Masterclass series. And thanks again. Goodbye.